Okay, boys and girls, 8:30, time to start. Let's see. Where did I put my notes here? I've lost my notes. Nope, that's not it. Oh, darn it. Here they are, I think. No, nope, that's not it. Okay, well, let me take a look at the. I had a little. I keep little post-its with all the things I'm supposed to be making. Okay, why is everything lagging so much? Okay, so it's the 22nd today. Chapter 4 homework is supposed to be due tonight. Has everybody got it done? Anybody need an extra day or two? I have no problem changing the date. We're not, I'm still going over the last of these example problems. Nope, everybody good? Okay. All right, so nobody, okay, we good. All right, good. So I'll just go ahead and let that happen. So that's that. And then what else is going on here? You got the feed the monkey thing. That's due tomorrow. Everybody can get that done by tomorrow. All right, so everybody's good with that. I didn't heard anybody there was one little issue that came up with that guy. That if you go to the Gizmo site, there's a whole bunch of different worksheets and things that you can go on the Gizmo site, and so people are getting confused as to which worksheet you're supposed to do. And don't do any of the worksheets that are on the Gizmo site because they're different than mine. Only use the ones that are linked in my Canvas assignments. Okay. Even if I use exactly the same worksheet that the Gizmo site has, I will post a link. I will just simply make a copy of it myself and post a link to that copy, on the Canvas, website, on the Canvas assignment in the instructions. Okay. So that was just a little bit of a confusion, but other than that, everything seems to be working fine. All right. Now, there is the issue of this Chapter 2 and Chapter 4, not Chapter 3 assessment. I've got it made up. It's just 10 questions, multiple choice. I'll probably give you 50 minutes to get it done. I don't know, maybe an hour because this is AP. And we got to pick a date next week to do it. So I was thinking, I don't know, Wednesday of next week. But it's kind of a ways off. But so can we just do Wednesday of next week for this assessment? And the way it's going to work is, it's going to be a timed assessment. So when you log on, you'll have, however many minutes, either 50 or 60 minutes to do it. I'll go back and look at the problem and see how difficult are they, how long would it take a person to do this. Most of the problems you should be able to figure out by looking at the book. The assessment is open book, open notes, open example problems that I do, open practice problems that I put up there for you, and it should be pretty much, you should be able to figure it out just by looking at that stuff. So it's not like it's a test like in class test, okay? And the only restriction is there's a time limit, okay? And I'll have the assessment set up so that you'll do it. You can take the assessment anywhere from 11 o'clock in the morning to 9 p.m. at night, but you have to make sure that when you start the assessment, you can devote the next 50 minutes, if that's what it is, 50 minutes to the assessment, because you can't pause it in the middle. Once you start it, you gotta finish it. So you just got to make sure that everybody in your house knows, hey, be quiet for the next 50 minutes because I'm doing an assessment. It's not going to be a whole huge number of points. It's only going to be 20 points, which is the same as all of the labs we're doing. So it's not like a huge part of your grade, but it's just like a little review assessment. Okay. So Wednesday sounds good. If you don't want to say anything in the chat, yes, it's multiple choice. Okay. If you don't want to say anything in the chat, you can send me a personal message saying, hey, that's a bad day for me because once I get off of school at 11 o'clock, I'm working for the rest of the day at a job. So I can change it and find another day. What day we do it next week is unimportant to me. Okay? Does that make sense to everybody? Okay, good. All right, so just two things I have for you today. I'm going to go over this, the last of the example problems on relative motion. And then I've got yet another lab for you using this gizmo stuff, okay? And I'll go over that a little bit because it's a little different this time. But it's mostly the same, but a little different. So I'll go over the details of that. All right? Okay, so let's head into this last relative motion example problem. Oh, by the way, so because this is literally the last example problem I'm going to do for the chapter. So this is the end of the chapter at this point. So I'm going to have that assessment next week, but I usually like to wrap up the chapter before moving on to the next chapter, previous chapter before moving on to the next chapter. But remember, we're online and we're in asynchronous mode. Okay, so I can kind of mix things around. So Monday, this is Thursday, so I won't see you till Monday. Monday we'll start chapter 5. Okay. All right. Okay, so here's the last of the relative motion example problems I'm going to do for you. You have two cars traveling towards an intersection, and you can see them in the drawing down there. They've set up an XY coordinate system. One car is moving in the negative X direction, one car is moving in the negative Y direction. You can see the speeds that are given there and the distances that are given there, excuse me. And, excuse me. And what are they asking? Okay, so in unit vector notation, what is the velocity of the motorist, that's the car labeled M, with respect to the police car, which is labeled P. So the velocity of the motorist with respect to the police car. Okay, does that sound familiar from what we've done before? Something is velocity is measured with respect to something else, which is moving. Okay. All right. And then they want that. Okay. So and then for the instant shown, does the direction of the velocity found in A compared to the line of sight between the two cars? If the cars maintain the velocities, do the answers to A and B change as the cars move near the intersection? Okay, so those are the kind of conceptual questions. All right, so how do we start this guy? First things first, this is probably the first thing you want to do in these problems, even though I didn't always do it that way. Is go back to that bus, and if you're lost, you go back to the bus analogy. It's your velocity relative to the bus plus the bus's velocity relative to the ground equals your velocity relative to the ground. And that works in both 1 dimensions and 2 dimensions. Okay, so this is 2 dimensions, obviously. And they're already asking for one of those things. They're asking for what is the velocity of the motorist with respect to the police car. So following that analogy, it should be the velocity of the motorist with respect to the police car plus the velocity of the police car relative to the ground. That should equal the velocity of the motorist relative to the ground. Okay? So there it is. And it works, like I said, it works in 1 dimension and 2 dimensions the same way. The only difference in 2 dimensions is you're doing vector addition, not scalar addition. Okay? Velocity of the motorist rather than the police car. Okay. Want to do a screen grab? Okay. All right. So is everybody clear on this equation here? The velocity of the motorist with respect to the police car plus the velocity of the police car relative to the ground gives you the velocity of the motorist relative to the ground. Okay. By this time, it should be kind of, I think you should see the, it's always, and it always works the same way. Okay. So we want this guy, but what are we asking for? We're asking for this guy here, velocity of the motorist relative to the police car in unit vector notation. Okay. Can we come up with these two guys in unit vector notation? Yes, right, and it's kind of like what we did. It's actually easier than what we did with the shopper and his daughter, right? In that one problem, because these guys are moving along the x and y directions, so it's actually easier to set them up. So, for instance, what would you write down in unit vector notation for VPRG, the police car relative to the ground? It's almost, it's not even a calculation. You just write it out. And yeah, you can leave it in 80. You can leave it in kilometers per hour because everything's in kilometers per hour. So leave it in kilometers per hour. So yeah, but it would be negative the 80 kilometers per hour times I. Yeah, and then in the y direction, it's very similar, right? All right, so I wrote down a little triangle there because that's also kind of helpful. And if you're uncertain how to write these triangles down, go with what you know. Like for instance, the police car relative to the ground. Well, that's got to be an arrow that's pointing in the negative x direction, right? And the motorist relative to the ground, well, that's got to be a vector that's pointing in the negative y direction. And you look at the equation up there, and it's a vector plus VPRG has to equal VMRG. So VMRG is the resultant vector in this addition. So remember, it's vector A plus vector B equals vector C. Remember how we did that when we did graphical addition of vectors? So this would be vector A plus vector B, and this would be the vector that completes the triangle because it's over here on the resultant side. That makes sense? And that guy has to be in the negative x direction, and that guy has to be in the negative y direction. So this guy's got to look like that. Not necessarily drawn to scale, right? Because in fact, I think I screwed this up a little bit. This should be longer than this one. It is slightly longer, but not probably as proportionately longer as it should be. Does that kind of make sense? All right. Now, okay, let me kind of skip ahead a little bit. Think of what it would look like if you're this guy and you're going this way, the police car is going that way. And think about a line drawn between the two cars. And because that's when you look at something, you're looking in a straight line. The light beams always travel in a straight line. We're not going to get into special relativity or general relativity, I should say, where we have curved space, and so light beams travel along geodesics, and therefore they curve around gravitational objects. We don't do that in this class. So light beams always travel in a straight line. So the light that you're looking at, that comes from this car, travels in a straight line to that guy. So as they're moving, that straight line's got to be a line that basically just connects the two police cars. That kind of makes sense? And so that line's got to be in that direction. That light beam's got to travel in that direction. Okay, so keep that in mind. All right. All right, so this one, hold on, I'm zoom out a little bit. Okay, so what I did is the same thing I did in the last problem. I'm interested in VMRP, so solve for it in the equation up there. Remember, you can. I think people at first glance when they start looking at this thing, and they, well, wait a minute, can I really just subtract a vector from another side? Because it's not like algebra. These are vectors. These are not scalars. But remember, when you subtract, you are actually what this is saying is you're actually doing a vector subtraction, not a scalar subtraction, a vector subtraction. So, I can go from here to here just symbolically, and it means, and you can do that correctly. If that plus that equals that in vector mathematics, then that should be equal to that minus that in vector mathematics. Now, how you evaluate this subtraction, that's a different story. That's different than how you would do it in scalar mathematics. So how we do it in vector mathematics is, of course, we add and or subtract the x components to the x components and the y components to the y components. You remember that stuff from vector mathematics. All right, so that's that. I explicitly wrote out the I component for the police car. Wait, police car relative to ground. Motorist relative to ground. Did I get this backwards? Hold on. Okay. Senior moment here. Police should be. What is relative to? Oh wait, I got those backwards. Huh. Those are. Yeah, I got them backwards. Wait, hold on. Okay, so the police car. Hold on. If I subtract this guy from both sides, it should be motorist relative to ground minus police car relative to ground should equal motorist relative to police car. Yeah, that's what I'm thinking. I think I got these backwards. I got this right. This is the motorist relative to the ground minus police car relative to the ground, but these letters are wrong. I got the P and the M reversed. Yeah, okay. Wow. Oh, let me fix this. It should be the motorist relative to the ground minus police car relative to the ground, because the motorist relative to the ground should be 0 in the I direction and negative 60 in the J direction. And the police car relative to the ground should be minus 80 in the I direction and 0 in the J direction. This is correct, but this guy was written down incorrectly. First time I spotted that. Jeez. Okay. So now does it make more sense? Sure, like people were like going, hey, wait, that's not what you just said. Okay. Anyway, I think I'm correct now. All right. So like I said, I explicitly put in 0 for this guy in the I direction, right? Let me go down a little bit. I explicitly put in 0 for I in that direction, and I explicitly put in J equals 0 for this guy, right? Just so you can see the components so that you can see how the addition and subtraction works. So it's going to be 0 minus a minus 80, right? 0 minus a minus 80. And then minus 60 minus 0, minus 60. That kind of makes sense? Just mathematically, does that make sense to everybody? Okay, and if you think about it, okay, we're looking at it from the motorist's point of view. So from the motorist's point of view, he's like his own fixed reference plane, his reference point, right? It's not a bystander standing on the road watching this happen. He's looking at it from his perspective and a reference frame that's attached to his car. So from a reference frame attached to his car, in the Y direction, which way is the police car moving towards him? The answer would be up, right? You think about a little XY coordinate system attached to M, and you only look at it from that point of view, the police car would be moving towards him, which would be up along the Y-axis, right? Is it making sense here? This is the mind-bending stuff when you try and think about, like, okay, what would it look like from a moving reference frame? And then he's from that same moving reference frame that's attached to the car M. The car would be moving in the negative X direction. Did that make sense? I don't know. This is the hard part to kind of conceptually understand. Okay. All right. No questions about that. We'll move along. Okay. If the cars maintain their velocities, do the answers to A and B change? Wait, where am I? Where did B go? Oh, for the instant. Hold on. Let me go down. Okay. For the instant shown in figure blah blah blah, does the direction of the velocity found in A compared to the line of sight between the car? I kind of answered that already earlier. And if you think about it, yeah, because that's exactly what VMRP is telling you. It's a vector. It's the velocity of the motorist with respect to the police car, right? And so you're asking how fast is the motorist approaching the police car in a straight line, right? So, and that's what a velocity vector tells you. It tells you how fast you're going and in what direction you're going. And you're going in a direction directly to, because that's what it was. That's what the whole thing meant. The velocity of the motorist relative to the police car, it's got to be the velocity in the direction of the police car. So that's the direction of the line of sight. So it's a little hard to explain. But does that make sense to everybody? It's kind of like if you had a little laser pointer, right? And you had it. You're not supposed to do this, of course. But if you had a little laser pointer and you're the motorist and you keep it continuously aimed at the police car, it would be a straight line between them, and that's the line of sight. And as they approach each other, if you point that laser pointer in a direction other than the police car, then it's not VMRP anymore. It's some other velocity vector. That makes sense. I don't know. That's the best I can explain it. Okay. Any questions? All right. Okay. All right. Last one. If the cars maintain their velocities, the answer to A and B change as the cars move near to the intersection. Okay, so if the answers to A and B change, if they change, then these numbers in this subtraction would change, right? That's what they're saying. If they don't change, though, if these numbers in this subtraction don't change, if that 60 stays the same and that minus 80 stays the same, right? Minus 60 and minus 80 stays the same. If those stay the same, then these two guys have got to stay the same, right? So VMRP has to stay the same in both magnitude and direction. That's for a vector to stay the same, its magnitude and its direction has to stay the same. Okay, so answers to A and B stay the same. So the answer is do the answers change? And the answer is no, they don't change because V PRG and V MRG are constants. If these are constants, that stays the same, so that stays the same. That VMRP is a constant velocity vector. Does that make sense? This is actually conceptually a difficult question to answer. Okay. Actually, it is because these are velocities and they're constant velocities. Well, wait a minute, wait. If they're traveling at constant velocities, then they're okay. So how do you measure? You're thinking in terms of the distances involved, okay? But you know, if you think about the ratio of the x position of this car to the y position of that car, since they're traveling at constant velocities, they should be proportional. Right? If one was accelerating, everything would change. But as long as they're traveling with constant velocities and the same amount of time changes for each car, the proportion, the distances from the origins should remain proportional to each other. So if the proportion of those triangles, it's like a similar triangle thing in geometry, right? Side, angle, side. Okay. The triangle between this, if you make a triangle out of the x-axis, the y-axis, and the line of sight between them, if you make a triangle out of them, remember this side, this 800 is going to get smaller, right? This 600 is going to get smaller, but in proportion to their velocities, right? So the proportions should stay the same. So, you know, from a geometry point of view, you know, side angle stays the same, side stays proportional. So you're shrinking the triangle down. It's a right triangle, and you're shrinking it down proportionally on each side. Did that kind of make more sense? And what I wrote down here maybe doesn't completely answer the question. Okay. The whole thing here is that everything's constant velocity. There's no accelerations. Which, by the way, that's all you're going to have to worry about. There is such a thing as relative acceleration, and we might get into it in later chat. And then guess what? It works exactly the same way. You know, if this were like the acceleration of the motorist, you know, with respect to the police car plus the acceleration of the police, it would be the same way. Okay, yeah. So it's the relative thing going on. That's the whole thing. It's really hard to understand this. It's like this relative to this and relative to that. And you get confused. The main thing is, you know, you look at this triangle here. You know, this MRG, that velocity vector doesn't change. That velocity vector doesn't change, right? So this angle here, you know, between that doesn't change. So, and this is the velocity of the line of, this is the line of sight, right? That's the line of sight between the two cars. Don't think about it in terms of distances. Just look at the velocities. That velocity doesn't change. That velocity doesn't change. So that velocity can't change. So the angles inside the triangle can't change. And unless the angles in the triangle change, the line of sight stays exactly at the same angle. Does that make more sense? Okay. All right. So any other, these are hard. These are not easy problems. Okay. These are really mind-bending stuff. But if you're having trouble, go back to first principles. Go back to the bus. It's your velocity relative to the bus plus the bus's velocity relative to the ground gives you your velocity relative to the ground. Okay. That's kind of the first thing you start with these guys. All right. Any other questions on this, or we'll go on to the next little topic here. All right. We're doing for time here. No, we're doing great for time here. Okay. All right. I'm going to get rid of this then. Okay. No objections. So ordered. Okay. All right. Next, I have another gizmo for you. Yay, gizmos. I'm starting to really like these gizmos. This one's kind of fun too. I think it's almost a little bit more fun than the monkey one. But it's another projectile motion one, and it goes over some stuff that I probably should have gone over in class, but you're going to learn it yourself. And it should all be set up right at this point. Let's see if I just double check myself here. Oh, they locked me out. Yes, okay. So hopefully, there's this again, it'll work a lot, very similar to what we did last time. There's a Canvas assignment, which I called, what did I call it? Golf range. Okay, so there's a Canvas assignment called golf range. And first thing you do is go to the Canvas assignment, okay, to get this thing started. And there's instructions, and this worksheet here, you download from the Canvas assignment. Again, there are a whole bunch of things, like on that HMH website. I hope you've been playing around with that HMH website and look at look at the simulations and some of the stuff, because there's some really good stuff on there. But on the Gizmo site, there are, and you have access to their worksheets, which are look like mine, because what I do is I take their worksheets and then I completely disagree with everything they've done, and I change everything because I'm like that. It's a character flaw of mine. I have to do everything my own way. So there, but I left all the thing at the top and a lot of the different stuff. So a lot of it looks the same way, but it's not the same worksheet. So I will always have a link in the Canvas assignment to the web worksheet that you're going to be filling in. Does that make sense? Okay, and it'll be like last time, or at least I hope I set it up right. And when you click on the link, it'll say, "Do you want to make a copy?" And you say, "Yes, I want to make a copy." That way, you have your own copy that you put your own answers in, and it doesn't corrupt mine. I think I got that set up right. Let me just double check that. Golf range. If I click on golf range, yep, copy document. Okay, so hopefully it's set up right. And you'll get your own little copy of this, and it's an editable Google Doc, right? Okay, and it says go ahead and get the golf range gizmo, but then you got to go back to this guy. Okay, go back to this Google Doc. And there's some stuff that you got to do prior to doing the rest of the, prior to playing with the gizmo. And part of it is reading part of your book, okay? So it says there, right there, there's a prior knowledge section with a couple questions. Go to your book, read your book. I think I got the page number right, 85, and there's a section on horizontal range and maximum height. And there's a particular equation called the range equation, which is labeled as equation 4.13. I hope I got that right. 4.13. Yes, I got it right. I'm having to double check myself at this point. And just answer the questions. I think they're pretty straightforward. And then once you answer these questions, you're going to go play with Gizmo, okay? And follow the instructions and put your answers in the box. Remember, this is an editable document. You can put your answers in the box, okay? And then just, like I said, follow through the instructions. Read them carefully. They're set up to work the right way. So one of the things that the gizmo doesn't tell you is how far you are horizontally away from the hole. So you're going to use your knowledge of physics to figure this out, okay? And so it says the numbers will vary a little bit because of you're going to basically change the angle that you hit the golf ball at into the air and change the initial velocity you hit it with. And so the numbers come out a little bit weird. There's a little bit of round off error in the numbers. So if you do it right and you round off to one, it should be a numbered followed by a couple zeros. I'll just give you that much, okay? Because that's the actual distance to the hole that they won't tell you on the gizmo, but you're going to figure it out, okay? Then what you're going to do is you're going to go back and recreate those projectile motion problems that we did when we were fired animals off of a building or a cliff horizontally. Do you remember those guys? No? Okay. And you're going to recreate that. Yes, exactly. You're going to recreate that with this little gizmo, okay? And what the thing that I think is cool about this is that there's a little box you have to check first, the advanced features. Oh, by the way, every time you do the gizmo, you have to hit the reset button to reset it. So or else everything is grayed out. So just remember you're going to be constantly hitting the reset button. So you set the golfer's height to 200 meters and then hit the angle to 0 degrees. So you're going to, the same thing as in those problems that we did. Okay, now, here's something that's a little bit different that we didn't do before. We'll see how it works. I want you to get out a piece of paper and a pencil, actual paper and pencil, and using the numbers that you came up with from the gizmo, write out very carefully and very neatly, because I'm going to be reading these, the exact same problem we did in it's almost exactly the same problem. Now, I'm not going to specify like a coordinate system for you guys. I'm going to let you guys do that yourself. And I'll be looking at them. Well, let me say this. Please only use either the top of the cliff or the bottom of the cliff for the origin. That way it doesn't get crazy. And I'm really serious about this. Write it out like formally, like this was like the free response question on the AP test, and they're grading you by rubric, because that's what I'm going to do. I'm going to grade you by rubric. Okay. And so, like I said, it should look just like how I wrote it out. Drawing, coordinate system, components of the vectors listed, kinematic equations, numbers, and unit substitution. You should be written down very formally, because you're going to make an image of this guy and paste it into this Word document. Does that make sense? Okay. Have you ever done this before? Is anybody like, I've never done this before, how do you do it? Okay. Now I'm sure there's more than one way of doing this, but the image has to be in the document, because you're going to make an image of the document and upload that to Canvas. Oh shoot! I didn't even paste in. Oh gosh. Okay, so I'm going to have to change this a little bit, because I need an extra 9 in there. Okay, and then. All right, so I got to go. I'll go quickly and edit that the document, because you're going to paste an image into the document, right? And then either make a PDF of it or whatever you have to do, and then upload it to Canvas. Now, here I don't know if you guys know this, but there's a cute little feature in Google Docs, and I put it over here. If you go in your Google Docs and you say insert image and then go down to camera, it'll actually, if you have, your web camera enabled, or if you have, I don't know, do it. I'm assuming the Chromebooks all have cameras, right? I mean, I don't know how anybody's doing Zoom if this isn't true. Do they? Please say yes. This won't work if it, yeah, okay. And then when you say insert image camera, a little pop-up screen, and it'll show you the web camera, right? And then you can just take your pen and your paper, hold it up to the camera, and then take a picture of it and paste it, and it'll automatically paste it into the document. Okay? That makes sense? It's a really cute little feature. All right. So any questions on that? Okay, I'm giving it till like when the 27th, which I think is next Tuesday. So I'm giving everybody I gave everybody a lot of time. Again, I'm experimenting with this stuff as we go along, so I'm just assuming there's going to be technical glitches. Okay. All right. And then, of course, the last thing, once you get you worked out solution, you'll have the initial velocity of the ball off of the cliff, fired horizontally. Plug that into the gizmo and see if you get a hole in one. You know, if the physics works out correctly, it should work, right? All right. So, any questions about any of this? No? Okay. Okay. So that's it for today then. I want you to spend the rest of the period trying this guy and seeing if it works. Again, if I'll be sticking around. You can message me through Canvas. I'll be watching my Canvas inbox, and if you run into technical glitches, okay? Okay. All right then, guys. That's it for today. Go off and have fun with this little gizmo thing. Oh, one more thing. Yeah, you'll see in the instructions. If you got to go back and look at that video of that one day I did those instructions, the link's in the Canvas assignment. So there you go. It's listed there. You'll see it. Okay. When it's not a test, no test, assessment, review assessment, and it's gonna. And I'm planning Wednesday of next week. Okay, you too. Have a great day, guys.